So chapter 4 goes over nuclear chemistry. We're actually only going to cover sections 1 and 2, and we're going to leave off the sections 3 through 6 as our standards don't really cover the rest of the chapter after section 2. But section 3 actually is an interesting section if you are interested in seeing some of the application of and measuring of radiation. But like I said, we're not going to go over that in this lecture. So we had discussed isotopes in the previous chapter. And so in this chapter, we're going to discuss specific isotopes that are radioactive. And so what it means to be radioactive is that the nucleus of an atom is unstable. And if it's unstable, then it's going to want to break apart in some way. So we find most of the radioactive isotopes past the number 20 of atomic number on the periodic table. um, so in order for the isotope to become more stable, it needs to emit some type of radiation. And so then everything always wants to become more stable. It doesn't want to be at high energy, so it needs to emit some radiation to kind of calm itself down. There can be, as we discussed in the past chapter, there can be more than one isotope of each element. And we have looked at some of the ways that isotopes are written. And this example on this slide shows iodine. We could see iodine 131 or I-131. And remember that 131 is referring to the mass number, or the number of protons plus neutrons, excuse me. And so if we were to write this in the other notation that we had went over in the last chapter, remember that when we put the mass number up on top, the protons plus neutrons on top, and then the atomic number, just the number of protons on the bottom, and then we use the atomic symbol. So in table 4.1, it shows the both notations of writing the isotopes, indicating their mass number. And we can see that we have the magnesium isotope 24 and iodine 127 as our stable isotopes, and uranium doesn't have any stable isotopes. And then they had the radioactive isotopes beneath. And so it just shows you the different ways that it's written. So what radiation is basically energy. It's an energy that calms the atom down, and so it emits some type of energy for that element or atom to become more stable. And so we're going to talk about the three main types of radiation. There are other types of radiation, but we don't need to cover that in this class. We're just going to go over the three main ones, the first of which is alpha particles. And alpha particles are the same exact thing as a helium nucleus. So helium is the second element on the periodic table, has an atomic number of 2, and it has also 2 neutrons, so it has a mass number of 4. And so you can see how the alpha particle is written there. The beta particles are basically high energy electrons. And since it's an electron, it has a negative charge. Since it's only an electron, it does not have a mass number. There's no protons and no neutrons. So it's a mass number of 0, but a charge of -1. And then lastly, we have gamma rays. And gamma rays are the highest in energy of the three. And it's really, really high energy, and it does not contain any mass. And so there's no mass number or atomic number. So there's no, there's going to be 0 as the mass number and 0 as the atomic number. And so here's just a table of all the different forms of radiation. And we're not going to go over the positron, but all the other ones are given. And so you can see the type of radiation, their symbols that they use, um, and the indication of their mass number and charge numbers. And then it also goes over how the nucleus changes. So the biological risks of radiation really comes from the ability of radiation to knock away electrons. So this radiation can come in and um, bump into these, other molecules in your body and form unstable ions. So these electrons are knocked away from the stable, normal molecules in our body, and so then once those electrons are knocked away, then they become unstable, and that instability then causes for further chemistry to occur, because when something's unstable, it wants to restabilize itself. So it's going to do whatever it needs to do in order for that to become stable again. And so one of the cases is like in water, where water loses its electron and then um, can then go through further chemistry in becoming stable again, and can cause other chemical reactions that could cause damage to cells. So these three different types of radiation have different amounts of energy. Alpha particles are low in energy, beta particles are a little bit greater in energy, and then gamma rays are much greater in energy. And so with the different amounts of energy, there's different amounts of protection required to block these particles. And so alpha particles, since they are low in energy, you do not need much in to protect yourself from these particles. And so it can be stopped with something as thin as a piece of paper. It can be stopped by your clothing. So it does not have much energy, so there's not much protection required. Beta particles require a little bit thicker of material to stop the particles from damaging you, or being able to penetrate and uh, get onto a person. So and that is because it has a little bit greater energy. So um, but it still can be uh, dealt with nothing that's irregular to have in a lab. So you can just stop it with a lab coat or gloves. Gamma rays are quite powerful and quite energetic, and so you need um, a pretty heavy duty protection from those. And so these are type of this is type of radiation where you would need some type of lead shield, or some type of concrete wall to protect yourself from being exposed to this radiation. Um, just as general safety measures, you can limit the amount of time that you spend near these radioactive sources, and then increase the distance from these sources. So if you can stay further away from it and spend less time with these radioactive sources, then you are protecting yourself as well. And so this is just a table showing the ways to protect yourself from these different radiations. And you can see that alpha particles, they can't travel very far in air, and they're not going to penetrate very far into your body, and you're very easily shielded away. Beta particles, a little bit can travel a little bit further, can penetrate your body a little bit more, and you need a little bit more safety measures to protect yourself, to shield yourself from these particles. And then gamma rays can travel quite far, can penetrate quite far into your bodies, and you need some pretty heavy duty shielding to protect yourself from them. So in our learning check here, it's asking what can we use to protect yourself from these following forms of radiation. So we said alpha particles very low in energy, so it can be stopped with something as easy as a piece of paper or simple clothing. But when we look at gamma radiation, very high in energy. You need some pretty heavy duty protection, so you would need something in the likes of lead vests or concrete to protect yourself. And so now it's asking us which form of radiation is emitted with a mass number of 0 and a negative charge. So we had looked at the three different types of radiations, and the one that had a mass number of 0 in conjunction with a negative charge was those high energy electrons or beta particles. And so here we see the beta particle and we see how it's written. We use the E to symbolize that it's an electron with a 0 mass number and a -1 charge. And so now we'll go into some nuclear reactions. So what is going on with these radioactive atoms, and how are they affected? What do they, what are they decompose to? So when we mentioned the alpha particle, when a radioactive element emits an alpha particle, it's going to lose that those pieces. It's going to lose that helium nucleus in a sense. So it's going to lose a mass number of 4, and it's going to lose an atomic number of 2. It's going to lose 2 protons and 2 neutrons. And so here we see this reaction of uranium-238, which is a radioactive isotope. And so when the uranium-238 emits its radiation, emits its alpha particle to become more stable, you see that it loses the 2 protons. And so it goes from an atomic number of 92 to 90. And then it loses 2 neutrons as well. So it loses a mass number of 4, so it goes from 238 to 234. So we're going to be asked to complete nuclear equations, and so just showing the process of the degradation of the radioactive isotopes to its more stable atoms. And so when we do this, we want to make sure that when we sum up the mass numbers on the left side of the equation, it's equal to the sum of the mass numbers on the right side of the equation. And same thing goes with the atomic numbers. We want to make sure that when we sum up the atomic numbers on the left side of the equation, they equal up to the sum of the atomic numbers on the right side of the equation. Now, so if we see here on the example on the bottom, we have californium-251, and it's degrading to curium-247. And to do that, it's going through alpha decay. And so on the left side, the californium has a mass number of 251. On the right side, curium has a mass number of 247, and the alpha particle has a mass number of 4. So when you add up 247 and 4, you get a total mass number of 251. So both the left and the right have mass numbers of 251. The same thing is done with the atomic numbers. So californium has an atomic number of 98. Curium has an atomic number of 96, and the alpha particle has an atomic number of 2. So when we add up the atomic numbers of curium, 96, and the alpha particle, 2, we get a 98. And so the left side and the right side both have atomic numbers summing up to 98. One other thing you want to pay attention to is that when californium degrades, it's losing 2 protons. So when it loses 2 protons, it is no longer the same element. Remember that each element is specific to a particular atomic number. And so the atomic number is no longer the same, so it becomes a new element. And so that's why it is now becoming curium. So here's just kind of a quick guide on the steps that you can follow. So you can first just write the incomplete nuclear equation. Just write down what you know, what you're starting with, what you're ending with, what type of decay you have. Then two, you want to determine the the missing mass number. So look at what isotope you start with and what isotope you are ending with. Look at what's going to be the difference. How are you going to get both sides to be equal? Same thing done with the atomic number. Then once you know the atomic number, you can figure out the symbol of the new nucleus, the new atom, and then lastly just complete the nuclear equation. So here's just an example of doing a nuclear equation and completing a nuclear equation. So it's asking us to write an equation for the alpha decay of radon-222. So first we're going to write the incomplete equation. We know we have radon. We know it's 222 of a mass number. And when we look on the periodic table, we find its atomic number of 86. Then we see that we have an alpha decay. So alpha decay, you use a symbol. It's the helium nucleus. So we have He, has a mass number of 4 and an atomic number of 2. So step 2, determine the missing mass number. So the left side has a mass number of 222. So we need the right side to equal up to 222. So we just subtract 4 from 222 and we get 218. Then we have to find the missing atomic number. So we have an atomic number of 86 for radon, and we have an atomic number of 2 for the alpha particle. So we subtract 86 from 2 and we're left with 84. Then we look on our periodic table and we look at where is the atomic number of 84, and we see polonium, Po. So now we can complete the last step by writing the equation out. So we have the radon-222 with the atomic number 86, and it's decomposing to the polonium, and we had the mass number of 218 remaining, and the atomic number of 84 remaining. And then we also have the alpha particle on that right side of the equation as well. So beta decay is slightly different, a little bit more complicated, I guess. So a beta particle is actually an electron emitted from the nucleus, and that electron stems from the decay of a neutron. And so if you remember, a neutron is a neutral charge. And so what actually happens is the neutron breaks down into this beta particle, this high energy electron, and then also a proton. And so the sum of the charges is still going to be 0. So the neutron is neutral or 0 charge, and then it's going to break down into an electron that has a -1 charge and a proton that has a +1 charge. So the -1 and the +1 cancel out. And so because of this, the problems writing the equation and determining the equation is a little bit more difficult. In this example here, we have carbon-14. It's a radioactive isotope of carbon. It can be used for carbon dating. And a lot of times they use carbon isotopes to track where organic chemicals are and breaking down in your body. A lot of biological studies use isotopic carbon. So it's not uncommon to see carbon used as an examples. But carbon-14, all right, if you look on the periodic table, carbon-14 has an atomic number of 6, and because it's carbon-14, all right, 14 is its mass number, so it's 14 mass number, so we have 6 protons and 8 neutrons remaining. And so when it goes through beta decay, all right, it's going to lose that beta particle, so it's going to lose a mass number of 0, and lose a -1 charge. And so if you look on the picture on the right hand side of the slide, we see that on the right side of the equation, right, that 14 is added to the 0, so we still have 14 of a mass number on both sides of the equation. And then when we add the 7 and the -1, 7 minus 1 is equal to 6. And so you have 6 on both sides. So we see here that the only thing that's really changing is our atomic number, and because our atomic number changes, we end up with a new element. And so if we were trying to find or write the equation for the beta decay of potassium 42, all right, we can just first write out the incomplete equation. So we have potassium, which is K, 42 is the mass number, so it goes on top. And if we look on the periodic table, K is found at number 19, so it's got an atomic number of 19. And it's a beta decay, so beta decay is written with the E, with the 0 mass number on top and the -1 on the bottom. And so the mass number for beta decay, the mass number is not going to change because we don't have any mass number for the beta particle, so it's going to remain the same. And then we have to find the missing atomic number. So here we have 19 on the left and we need 19 on the right. So you can set it up to be 19 is equal to x minus 1, or you can just add the 1 to the 19 and you both find the atomic number of 20. And so then when we look at the symbol, what symbol belongs with the atomic number of 20, we can find calcium. And so when we complete the nuclear equation, all right, we just put all those numbers together with calcium and put that where our missing spot was in our equation. And so here, learning check, we're going to try to write the nuclear equation for the beta decay of cobalt 60. So to start off, you want to remember cobalt 60, you want to find its atomic number. So you look on the periodic table and you find that the cobalt CO has an atomic number of 27. And then it's beta decay. So we know that we're going to have use that E with the 0 mass number and -1 charge. So we're just going to go on to the next slide to kind of just see it. All right, so remember that when we have our beta decay, our mass number is going to be the same, all right, because the beta particle does not have a mass number. And then we just need to add 1 to the cobalt atomic number to find the missing atomic number for the new element. And so that brings us from 27 to 28. And then when we look for 28 atomic number on the periodic table, we find Ni, or nickel. So then we can complete our nuclear equation written here. So the mass numbers are equal for cobalt and the nickel, and then our atomic number goes up by 1 from cobalt to nickel. So in gamma radiation is very high energy and it's emitted from an unstable nucleus, and usually you'll find this indicated by the letter M after the mass number. And so when we have gamma radiation, it's just a gamma ray. There's no particle being emitted here. And so the radiation does not have a change in mass number or a change in atomic number. So we're just indicating the mass number of the original isotope with the letter M, and then it's losing that instability by emitting energy in the form of the gamma ray and making the pretty much the same isotope with just less energy. So here's this nice little table kind of showing you visually the different sources and um, what's going to change with the new element. And so it can be a little shortcut if you're doing homework, but you know you're not going to have this table on your quiz or test, so you want to just kind of remember how to do this. What we can also do with radiation is bombard particles or bombard other elements and atoms. And what that's just basically doing is speeding up these particles, smashing them into a stable atom, and creating a new nucleus, a new atom. And then oftentimes you have a part that does not stick all the way. And so we call this process transmutation. You're transferring and changing and mutating this atom. And so here we have an example where we are kind of shooting a alpha particle at this boron nucleus, and when they hit, most of that alpha particle sticks onto the nucleus, but it does lose one neutron. And so we form a new nucleus, gaining mass and gaining atomic number, but loses a neutron. So it's just saying the same thing here. So when you want to notice that both on the left hand side and the right hand side, when you sum up those mass numbers, right, when we have the helium, the alpha particle, and the boron, we add up those mass numbers, it sums up to 14. When we do the same thing on the right hand side, when we add up the mass numbers of nitrogen and the neutron, we get 13 plus 1, which is 14, so they are still equal on both sides. We do the same thing with the alpha particles. We have the helium of an atomic number of 2 and the atomic number of 5 for boron, so they sum up to 7. So that's for the left-hand side. And when we look on the right-hand side, nitrogen has an atomic number of 7 and neutron is 0, so 7 plus 0 is 7. So we have 7 on both sides of the equation. And so here's an example when we bombard it with a neutron. And when this happens, it's going to emit an alpha particle, and we want to figure out what's remaining. All right, so when we add up the mass numbers on the left-hand side, we have 1 plus 59, which is equal to 60. So on the right-hand side, we have 4, and so we would have to have something added with 4 to equal to the 60 on the left-hand side. So that would be a remainder of 56. Then we have a sum of 27 of atomic number on our left-hand side, and we only have 2 on the right-hand side. So we need find what the number would be needed to add up to 27. So it would be 25 plus 2 is equal to 27, which would equal on both sides. And so then when we look on a periodic table and look, oh, what has an atomic number of 25? We would find manganese. So manganese, Mn, and then we would find the 25 as our atomic number, which we've written on the bottom, and then 56, which would be our mass number, written on top. And so that's what's done here, and kind of showing you the different steps. Okay, and so you can use that to kind of follow through. And so we get what we had discussed and found from the other slide. And so that concludes what we are responsible for knowing in chapter 4. And so I will post some problems that I'll work through and kind of go through the same steps, and so you can have some further practice and visualize how I set it up step by step.